Okay, all right. So let's remind you of the kind of things that we have done and where we are headed. And so the best way, I think, to look at the remainder of the course is to look at the amplifier that we've just studied and look at what are the problems associated with this amplifier. And in an attempt to solve those problems, we'll go towards new amplifier configurations here. All right, so let's keep that in mind. Okay, so this is the amplifier that you're all familiar with. This is the amplifier that we started with. Very simple amplifier. Common emitter amplifier, biased through an RB here, and using capacitors to couple in the signals here. And there were problems with this particular amplifier. One of the problems that we are familiar with is that this particular circuit is very sensitive to beta. The bias current ICQ is determined by the base current. ICQ is beta times IB, and IB is fixed through RB. So although IB does not change because IB is decided by RB and the supply voltage, the ICQ being directly dependent on beta varies with the beta, and therefore everything in the amplifier varies here. So in an attempt to solve that particular problem, you would have seen these two solutions. A solution here where we don't use any RB here at all, and we use a negative power supply, and that allows us to define collector current in terms of emitter current, and it has very good beta stability. If you don't want to use the negative supply voltage, then we said we arrived at this particular configuration where through a proper choice of RB, R1 parallel R2 with respect to RE, one can again achieve better beta stability. So in an attempt to overcome problems with this particular circuit, we arrived at these two. Now, all three of them have certain problems. And in an attempt to overcome some of those problems, we arrived at this one. We said that the emitter resistance that we are putting here and here, a part of the emitter resistance, if we leave it unbypassed, it results in several advantages. It allows us to obtain high linearity, better swing, lower distortion, high linearity and all of that, high input resistance, and higher input voltage you can apply, and the cutoff frequencies are also improved. So all those advantages come when you leave a part of emitter resistance which is unbypassed. Of course, what you're doing is you're sacrificing gain in the process. So we arrived at this particular configuration in an attempt to solve a certain set of problems. Major problem was that my original amplifier is highly nonlinear. It has very high distortion, and in order to reduce distortion, we said we can incorporate negative feedback due to RE, and that's how we obtain high linearity. And we get further advantages which are listed here. So we arrived at this particular one. There are all three of them, if I take along with these are all of a similar nature. They solve certain problems. There are further issues with it. One of them we'll look at is that this particular amplifier, we'll just see in a minute, has, if you want high gain, you will require very high supply voltage. Or let's say if you have a portable application and the supply voltage is very low, let's say VCC is only 1.5, then you get very low gain. So that's the problem with this particular stage. And in order to overcome that particular problem, we'll see a configuration like this here, where we'll replace the collector resistance by a transistor itself, and we call such a transistor as a transistor with active load. A resistor is a passive component, and so this is a common emitter amplifier with a resistive load here, and this is a common emitter amplifier with an active load here. So we'll arrive at that particular configuration in an attempt to solve the problem of obtaining high gain without requiring high supply voltage. Okay, that's the problem that we are. When we solve it, we'll arrive at this particular configuration. Another problem, all these amplifiers that you see here, they use capacitors. Coupling capacitor here, bypass capacitor here. They all use capacitors. And we'll see, I've talked about it earlier, capacitors are something that you can't make on a chip. Capacitors of microfarads you can't make on a chip, and therefore these configurations that you see here, they're not suitable for on-chip implementation. And therefore, we are looking for a configuration where there are no coupling capacitors, no bypass capacitors. In an attempt to solve that particular problem, we'll arrive at this particular solution that you see here, differential pairs. They are a natural solution to that particular problem here. All right, so we have seen these two. Then if I look at this particular, again, all these common emitter amplifiers, what we find is that we saw that there's a gain bandwidth trade-off. And one of the reasons for gain bandwidth trade-off is there's a capacitor here between the base and the collector, which is C mu. And as I increase the gain, if you recall, due to Miller's feedback, the capacitor itself gets multiplied by the gain of the amplifier. So that's one of the disadvantages of common emitter amplifier. So in order to solve that particular problem, we'll look at a common base configuration, which may be useful for us. Then if we look at this particular amplifier again, if we want to drive load which are very low, a loudspeaker may be 8 ohms or 10 ohms, and some other loads may be very small. So if we try to use a common emitter amplifier and we have to drive a load which is very low, we'll encounter lots of problems. And in an attempt to solve that one, we'll arrive at common collector amplifier. Okay, so each one of these configurations that you see here, which is the topic of next several lectures, devices with active load, differential pairs, common base, common collector, all of these arise in an attempt to solve problems which are there in our existing common emitter amplifier. Okay, so we'll discuss these in a little bit more detail in today's lecture. And as you would expect, so we arrive at these ones. As you would expect, each one of these will in turn have a problem of their own. A differential pair will have a problem of its own. A common collector will have a problem of its own. And so what would happen? We'll have new circuits to overcome those problems, right? So we'll have something, we'll see common base has its own problem. So how do we overcome problems associated with common base? And so that would be the topics of subsequent discussion here. So that's how we're going to proceed. So let me start with the first problem. The first problem is, how can we obtain higher voltage gain without requiring very high supply voltage? Okay, so this is our circuit. Whether I add an emitter resistance and all of them have the same problem. So we know that AV is ICQ, VT, RC parallel RL. And we know that the magnitude of AV will always be less than ICQ, RC by VT. All right, so that we know. As an example, if I require a gain of 1000, I will require VCC larger than 26 volt. Right? A large gain, that's what I'm trying to tell you. A large gain would require, you can just put it here, ICQ RC is 1000 multiplied by, gain is 1000 multiplied by VT, 26 millivolt will give you ICQ RC of 26 volt. And therefore VCC has to be larger than 26 volt. Alright, that's one way of looking at it. The other way of looking at it is, say I don't have 26 volts, suppose I have only 1.5 volt. What is the highest gain that I can get? So ICQ RC obviously has to be less than 1.5, and so 1.5 divided by VT will tell you that 1.5 divided by VT is around 46 or so. So that tells you AV is less than 50. The maximum possible gain that you could hope to achieve with 1.5 volts using this configuration is maybe 40 or 35 or something like that. So you are seeing the problem that we have with a configuration like this. High gain will require very high supply voltage, or if you have low supply voltage, you're limited in terms of the gain that you can get. All right. So what we are looking for then is, in an attempt to solve this particular problem, what we are saying is, can we replace RC? See, all the problems are coming because of RC that you see here. Can we replace RC by a new element? By a new element X, some new element that is there. It could be 2 terminal, 3 terminals or whatever, such that we don't end up with a problem like this. That's the question that we are asking. Now, what is the problem? Well, suppose we have an element X here. Whatever element X is, if we build the small signal equivalent circuit here, instead of element X here, we'll have its small signal model of element X. And we have seen no matter what element, 2-terminal element you put, a small signal model is nothing but a resistor. A 2-terminal element, non-linear, whatever it is, will be a resistor. So what we are saying is, in this case, AV would be GM, not RC, but it would be GM times RX. RX is the small signal resistance of that particular stage here. So what are we looking for? We are looking for an element X such that a small signal resistance Rx is very high, right? Because so that you can get very high gain. So Rx is very high, but at the same time, the drop across the element X is very low. DC drop across the element is very low. Because supply voltage is what? VCC is the drop across this particular element plus VCEQ. So what you're looking for is an element with a large small signal resistance Rx, but a small DC drop. Now with a resistor, obviously it's not possible. If you're looking for a large small signal resistance, you will require a large RC, and a large RC means large drop. So a resistor does not satisfy this constraint. So which element can I put here such that it has very high Rx, but the DC drop across it is small? Okay. If we look for, so this is what we are looking for. If we look for it, we find that the transistor is ideal for us. Look at it. Say I have a transistor and I bias it somewhere here. If I bias my transistor here, can you see where the DC drop is? How much is the DC drop? Look at that here. 1 volt, right? 1 volt or so, DC drop here. I bias it here. What is the small signal resistance at this particular point? The small signal resistance means what? The slope. The slope of this particular line is practically 0 or very small, which means that the resistance is very high. So transistor itself is an element. The drop across the transistor need not be very large. It's a fairly small. I can have a transistor biased in active mode with 1 volt drop between collector and emitter. And its resistance is very high. Its small signal resistance is very high. So the issue is, why not take this particular element X and use a transistor instead of it? The drop across the transistor would be small, and it will give us a very large value of Rx here. So that's the motivation for going towards replacing the collector resistance here by an element X with these kinds of properties. And what we are finding is that transistor may be a suitable solution here. So let's look at that then. All right, so what we are looking for is replace this by a transistor, element X. So how do we do that? One possibility, it may come to your mind that, okay, I take my transistor, this X out, and I replace it by a transistor, Q2. And Q2 also, remember, has to be biased in active mode. And so we have R1 and R2 that you see here. They are used to bias Q1 also and Q2 also. Let's not get into the details of, we can select R1 and R2 to bias it, all that. But let's not worry about the biasing part. Will this solve a problem? We are looking for gain at this particular point. Will it solve a problem? Will we get, remember what the issue is? The drop across the transistor is how much? 1 volt. If this is VCC here, the emitter voltage, whatever, I can keep VCC minus 1, and 1 volt will keep my transistor in active mode. So that's not a problem. The drop across it is very small. We can keep it very small. But will the resistance of Q2 be very high? Will I get high gain? Well, how do we do that? Let's build the small signal model. So when we build a small signal model, let's capacitors, let's put short, VCC ground. We get a circuit like this. All right. Circuit of this kind. This is our load resistor here. Note that R1 gets shorted out, VCC is ground, and capacitor also ground. R1 gets shorted out. R2 will come here. This is our R2 here, and Q1 and Q2. Now, how do we solve a problem like this? Can everybody see that this part, where are you? When you look right, what do you see? You're looking into the emitter. And when you look into the emitter, what do you see? 1 over GM. So when you look into the emitter, this whole part, 1 over GM, and load resistance is usually much larger than that. So, it doesn't matter here. So you get 1 over GM. And this is GM here. So that's the equivalent circuit that you get. And what is the gain that I will get? GM1 multiplied by 1 over GM2. And note, both the transistors are connected in series. They have the same current. Same current means GM1 is same as GM2. And therefore, you'll end up with a gain which is practically 1. So we replace the load here by a transistor in this particular manner here, but we don't end up with high gain. Remember what our motivation was, to get high gain. And what I'm getting is, if you look at it here, GM1 multiplied by 1 over GM2, I'm getting a gain of -1. I'm not getting high gain. What is the mistake I've made? When does a transistor give you higher gain, a higher resistance? We're looking for a transistor with very high resistance. When does it give you high resistance? Look at here. When I look into my transistor from the emitter side, what do I see? Very low resistance. If you don't have RB, you have R pi by beta, which is very, very low resistance here. When do I see high resistance? When I look from? No, even higher. When I look from the collector. When I look from the collector, note the whole thing appears as R0. R0 is very high. When you look from the base side, see, there are three things we saw in our last mini quiz. If you look at a transistor, when you look at it from the emitter side, you see R pi by beta. When you look at it from the base side, you see R pi. And when you look at it from the collector side, you see R0. The highest small signal resistance that you get when you see a transistor from the collector side here. So our mistake was that when we collected this particular transistor here, my lower transistor, it's seeing as a load this one Q2, but it's seeing into its emitter. And when you see into its emitter, naturally, its resistance is very small and you don't get any gain. So what we are looking for is using a transistor, but in a way such that it offers a high resistance at this particular point. So we can't connect the emitter of that particular transistor here. We need to connect the collector. We need to connect the collector here. Can I do that? I connected the collector here. Can I do that? Obviously not. It's pointing here. The current has to flow in the same direction. I can't do that. I need to connect the collector at this particular point. But then if I just take an NPN transistor and I connect collector here, then the emitter would be here. And then it doesn't make sense because we want the current to flow here. So it doesn't make sense. You're right. So what we need to do is connect it in this manner here. So now you take a PNP transistor here. In PNP, the current flows from emitter to collector, and then you have connected to this particular stage. Now you have connected to the collector end. All right. For sake of simplicity, I've left the biasing part. I've just said we have a current source available here, which is biasing it. Okay. So we don't worry about it here. And we'll apply some voltage here to bias this particular transistor in active mode also. Okay. So biasing part, we'll get into that later on. So what we are seeing is that we can take a common emitter amplifier. If you want to replace your RC by a transistor, then the natural choice is a PNP. You can't do it with an NPN. We just saw. If you connect an NPN, the emitter comes over here, and then you see a very small load. So you have to connect a PNP transistor here. All right. So now let's take this particular stage with a PNP stage here, and suppose I analyze it now. So again, so we are assuming that this current source will bias this particular transistor, and this bias voltage will also bias this one, and they are in series, they are carrying the same current, so we'll not worry about the biasing part here. Small signal circuit would be here, and so note that the Q2, if I look at Q2, I'm looking into the collector here. The whole of Q2 can be replaced by an R02, because when you look at a transistor from the collector side, base is ground, collector is ground, it appears as a resistance of R02, and this is Q1 here as it is, and so we can write the gain as GM R01 parallel R02. Now remember, so far we have been neglecting the R0 of this particular transistor. And why were we neglecting R0 of this particular transistor? Because R01 was coming in parallel with RC, and RC we said was much smaller. But now we don't have RC, we have a very high resistance, R0 itself. So R01 you can't neglect anymore. You have to take into account the output resistance of this particular transistor. So the gain of this whole stage becomes GM R01 parallel R02. And this is a very large quantity. R01 is large. We have seen early voltage. So let's look at it here. R01 is early voltage of the N-type transistor, NPN, VAN by ICQ. R02 is early voltage of the PNP transistor, VAP, by ICQ here. And then if I multiply them together, I get gain, which is equal to 1 over VT, VAN, VAP, VN plus VAP here, as some average value of the early voltage here. Now, look at this particular expression here. AV is this one here. Let's write it down here. So this is what we find for the active stage. A transistor with an active load. Active, why are we calling it? Because it's an active element. It's a transistor. In place of the previous one, which was a collector resistance, which was a passive component, we have replaced it with an active component here. What is the gain of this stage? VAN, VAP, VN plus VP 1 over VT. Now, what do we note about this? Do you see anywhere any dependence on collector current, ICQ? Is there any dependence on ICQ? None. No dependence on ICQ. Is there any dependence on VCC? There's nothing VCC here at all. All that I have to do is, note, I must have sufficient VCC to keep Q2 and Q1 in active mode. That's all. How much do I need to keep Q2 in active mode? Well, we've been saying more than 0.2. But to be on the safe side, let's say I require, you want some swing also, I require maybe, say 0.7 or 0.8 to keep Q2 in active mode, maybe 0.7 or 0.8 to keep Q1 in active mode. And all I need is 0.7 plus 0.7 or 0.8, 1.5 volt. All I need is 1.5 volt to keep Q2 and Q1 in active mode. And with 1.5 volt supply voltage, both of them are in active mode, and they will give me a gain like this. And let's put in some numbers here. Let's say early voltage of N-type, NPN and PNP is a reasonable number, 100. What we get is a gain of 1.9 into 10 to the power 3. We get a gain which is 2000. We get a gain which is 2000 and supply voltage is 1.5 volt. All right. So you can see the power of this particular circuit here. Very high gain and at 1.5 volt. If you recall earlier, we were saying that if you want a gain of 1000, we were requiring 26 volt here. 26 volts there. Now with this stage, we are saying gain of 2000 and at 1.5 volt and independent of supply voltage. All that you have to do is keep Q1 and Q2 out of saturation. That's all. Okay. So very nice stage, and that's why you would see that most of the amplifiers that you would encounter, or most of the IC amplifiers, monolithically implemented and all that, most of them will have a load which is an active load. Okay, we'll have an active load here. So we'll see these things in more detail later on. Okay, so a very nice stage where you replace RC by a transistor here. And note the other thing. Remember, to get a high input resistance, what were you requiring? A low ICQ. Now, I can take these two transistors and bias it at low ICQ. Will it affect my gain? It won't affect my gain at all. Gain has no ICQ dependence. I can bias it at low ICQ and get high input resistance, and gain is not affected. Gain is still the same. All right, so those are the other benefits that we get of this particular stage. There are problems, as you may imagine. There are problems with this particular stage, which we will talk about a little later on. Some of the problems are associated with biasing. And let me just hint at it. I'm saying Q1 and Q2 are both in active mode. They have to be in active mode. Then only you get high gain. If one of them goes into saturation, either Q2 or Q1, you won't get any gain. So both of them are in active mode. Now, when I go back and let's see this transistor in active mode here. Let's go back and see a transistor in active mode. Here is a transistor in active mode. What do you see? You see collector current here and you see collector voltage here. Collector current is almost independent of voltage. When you see a current which is relatively independent of voltage, what do you call it? A current source. You call it like a current source. So now, with that in mind, let's go back and think about what we are asking our transistor, what we are asking here. You're asking, this is a current source, and this is also a current source. Q1 is like a current source and Q2 is also like a current source. What is the value of the current? Who decides? This bias voltage will decide the value of this current, and whatever you do here will decide the value of this current. Now, when you connect two current sources in series, it's like taking two voltage sources in parallel. And if they are a little bit different, what would happen? If you connect two voltage sources in parallel, if they're a little bit different, what would happen? Similarly, two current sources which are in series. So, real life, obviously, you know that you cannot make them exactly equal. So let's say this is 1 milliampere and this is 1.1 milliampere. So this transistor Q1 is saying I want 1.1 milliampere and Q2 is saying I want 1 milliampere. What would happen? Q2 is saying I want to drive 1 milliampere and Q1 is saying I want to drive 1.1 milliampere. What would happen? Two current sources in series. All right, so we'll see that as a problem later on. What you would find is one or the other transistor in general will leave the active mode. One will win, the other will lose. Okay, one will win, the other will lose, and one of them will go into saturation region. And let's say Q2 may remain in active mode and Q1 may go into saturation. So Q2 wins and remains in active mode, drives the current here, and Q1 accepts whatever Q2 drives. But then we lose. We want both the transistors in active mode. Then only we get gain. So this is a problem that would occur because this is a current source and this is also a current source. You're trying to make two current sources in series. Okay. So I'm just hinting at the problem. There are ways of correcting it. We'll see that later on. Another solution that you might remember what we were looking for. We were looking for an element here which has very low voltage drop, DC voltage drop. DC voltage drop was very low and the small signal resistance or AC resistance was very high. Well, an inductor is also a solution. If I take my RC out and I put an inductor here, the DC drop across the inductor is zero. The DC drop across the inductor is zero. And if I choose my inductor properly, its impedance, is omega L, and omega L may be much larger than RL. So if I choose that, omega L much larger than RL, then that also satisfies my need. So the DC drop is small, omega L, the impedance of the inductor is very high, and you know that this comes in parallel with RL, so it doesn't really matter. My gain will get decided by RL here. Except that if I start putting in some numbers here, say RL is 1 kilo ohm, F is 1K, then L comes out to be very high. And very high inductors means they become very large and bulky and all of that. But that's the solution. This is only when I put 1K. Note that if the frequencies are high, for example, if omega is 100K or so, then the value of the L becomes smaller, but still it's a large, bulky inductor here. So inductors, as I've said, you can't really make inductors on silicon. So it's not suitable for IC amplifiers, but if you go back in history, you find, for example, this is AM radio receivers, the earlier radios that used to be there, you would note that a lot of transformers and inductors everywhere. Pocket radios means they have to run on 1.5 or 3 volt battery here. So you're looking for enough gain at 3 volt. You can't use resistors, RC. So what do you do in those times? So a lot of, you can see here, use of transformers, inductors, and all of that here. So you can imagine that I can use I'm saying an inductor here, I can use a transformer. So transformer would couple it to the next stage here. Gain from one stage to the next stage here. So that's a solution, but it's a solution which is, if you're looking for an implementation on an IC, then it's not a suitable solution. Okay? But that's an alternative that you should be aware of. All right, let's come to problem number 2. So we've looked at one problem here. Let's look at problem number 2. This is something that you must have encountered by now, that when I'm trying to get high input resistance, what I'm getting is this RB comes into play here. RB comes in parallel with R pi. And why is it a problem? Well, in order for RB not to pull down my Rin, what I need to do is make RB large. RB 10 times or 20 times or whatever, I need to make RB large here. And when you make RB large, we said that the emitter voltage here gets decided by this quantity XB that you see here, which is RB by R pi. So emitter voltage here becomes large. And when emitter voltage becomes large, it takes away the voltage from VCEQ and ICRC. It takes it away from there. So I have less voltage available for swing and less voltage available for gain. So that was a problem with R1 and R2 being creating a problem because they shunt my input resistance here. So is there a way of eliminating RB? The answer is yes. We can go to a solution like this where I have no RB. But we have a negative power supply. So we can eliminate RB, and now note that nothing comes in parallel with input resistance here. Input resistance is, when I look from here, is R pi. And I have no RB which is coming in parallel with this. But I have to use a negative power supply here. Now, what is the problem with negative power supply? Apart from the fact that I have to use one more power supply here, note that the current that you have, it starts from here, ICQ, and then is the same current flows here into VE here. So earlier, if you were using 5 volt power supply, now using plus 5 and minus 5 here, so the same current flows here, so you're doubling the power dissipation also. Earlier, let's say 1 milliampere current was being drawn, and you have 5 volt, so 5 milliwatts of power was drawn from here. Now, same 1 milliampere flows here, another 5 milliwatts of power is drawn here. So you're doubling the power dissipation here. So you're using one more power supply, and you're doubling the power dissipation in your circuit. And note that, in general, when you increase the supply voltage, you also want a higher swing so that you can deliver more power to the load. Because note that if I increase VCC, let's say I keep ICQ constant, collector current constant, and I increase VCC. So what am I doing? The power that is drawn from the battery is ICQ times VCC. So I'm increasing the power that I'm taking from the battery here. Now that's meaningful if I can deliver more power to the load. I'm taking more power from the battery, delivering more power to the load. But if I'm not, and how do you deliver more power to the load? Well, by building more swing. By building, because note that power dissipated in RL is V0 square by 2RL. So you want to build more swing. So if you're increasing VCC and you're increasing the swing also, then maybe there's some justification. I'm taking more power from the power supply, also delivering more power to the load. But note here that when I added more power supply here, I'm not able to increase the swing of my amplifier. If by adding a negative -5 here, if my swing could have also gone to a large negative value here, it would have been fine. But I can't increase the swing because if you look at this particular circuit, this is 0 in DC, and so this is -0.7. So this end of the emitter is fixed at -0.7. Emitter end is fixed at -0.7, and I have to maintain the transistor in active mode, and therefore, on the lower side, my voltage here can only go as close as -0.7 plus 0.2, so -0.5. So on the lower side, it can only go to -0.5. Although I may have on this side here -5 volt available, but my swing here cannot go to -5. Because this voltage is -0.7 here, is fixed here. So all that supply voltage is all being wasted. I have a -5 volt supply here, and all this that you see here is not available for swing. It's just being wasted. So that's not a good feature here. So although partly we have solved the problem in the sense that we don't have an RB, but we have created another problem. We have more power dissipation. We don't have a very good negative swing. So those are things that need to be looked at here. All right. Third problem. So we're looking at various problems that are there, and as I said, new circuits are arising out of an attempt to solve those problems here. Third problem. So this is the one of the common emitter schematics. As I said, look at all the capacitors that are there. So what we are asked, and the capacitors are there. We have R1, R2, all these RE that are used for biasing, and we know that we need to bypass the capacitor here. We need to couple it here and couple it here. So what we are saying is, can I If I want to make this amplifier on an IC, on a piece of silicon, I can't make these capacitors here. Okay, so why I can't make these capacitors? Some quick calculation. So one of the ways in which you can make a capacitor is you can take, let's say if you have silicon, you can make SiO2. It's an insulator, and you can put metal. I'm doing some very simple crude analysis, yeah? But one of the ways in which you can make a metal is the silicon acts as one plate of the capacitor, the metal acts as another plate. So it's a parallel plate capacitor. And let's see if we can, what kind of capacitor I can get. So capacitance is the E oxide by T oxide, oxide thickness here, multiplied by area. All right. So the dielectric constant of silicon dioxide is 3.9. This is E naught, which you're familiar with. Let's say I use a thickness, I'm using some typical values, let's say 200 angstrom, 20 nanometer thick silicon dioxide. So if I calculate how much do I need for 10 microfarad capacitor, I need 57 centimeters square. Very, 57 centimeters square. So you can imagine how large that would be of silicon just to make a capacitor of 10 microfarad. So all that it is doing is, this simple calculation is illustrating to you is that I can't make capacitors in microfarads range. The area required is simply huge. I can't do that. So then you would say is, why not make very small capacitor here? So I can make the area very small, and then what would happen is the capacitors would become very small. They'll go into picofarad range. And then picofarads range, what would happen is, you know that the lower cutoff frequency would become very high, because lower cutoff frequency is inversely proportional to capacitance here. So that's the problem. I can only make capacitors in picofarads range on chip, 20 picofarads, 30 picofarads, 100 picofarads, but they result in unacceptably large lower cutoff frequency. So the issue is then, what we are saying is, if you want to implement the entire amplifier on an IC, on a piece of silicon, you have to get rid of these capacitors. You can't make these capacitors. So let's look at a solution where we eliminated some of the capacitors. So here we required CB, CC, and CE. We require all these three. But remember, we had a solution where we just saw we can take the signal, directly couple it in. And so output also can go directly into the next stage here. So the coupling capacitors that you see here, we can eliminate through this configuration here. But bypass we need. If I remove this bypass capacitor, let's remove it. If I remove it here, you know that the gain will become GMRC by 1 plus GMRE. And if you try to bias it properly, you'll find that GMRE is much larger than 1, so it comes out to be RC by R. And I can multiply both sides by ICQ, so it's ICQ by RC, ICQ times RE. What is ICQ RC? The drop here is comparable to VCC, and ICQ RE, the drop here is comparable to the negative power supply. So what you end up is getting a gain which is close to 1. You can't build up gain. So if you eliminate a capacitor directly from here, so we don't use any capacitors, I end up getting gain. I can't build large gain in my circuit. Gain would be very close to 1. So the issue is then, but I have to get rid of the capacitor here, because this capacitor I can't build on piece of silicon. I have to get rid of it. So in that context, what do I do then? If I remove capacitor, the gain is going to 1. So obviously I need to connect something here at this particular point. Because remember, what are we trying to do? We are saying we need RE for biasing. And we need substantial RE for biasing properly. But under AC or small signal analysis, we need this particular point. If you go back, we need this point to be ground. AC ground or small signal ground. We need this point to be small signal ground. Or, small signal ground, you know that you don't get small signal ground. What you get is a CE, what does it do? It provides a very low impedance. So let me reframe the question and say, what you're looking for is under small signal condition, you're looking at this particular point, a very low resistance. Very low resistance at this particular point here. Low resistance, low impedance, whatever you call it. At this point, you need very low impedance here. But whatever you connect here should not disturb your biasing. Biasing should still occur properly. In that context, you've already seen the solution in our midsem, a circuit like this. We had this particular problem. Note, there are no capacitors anywhere. Can you see RE? But I've not connected any bypass capacitor. And many of you got the answer right. The gain of this particular stage is 0.5 GMRC. Half GMRC. All right. Which means what? Yes, I lose gain. As you can see here, if I had bypassed it, I would have gotten gain, which is GMRC. Here, I'm not using any coupling capacitors, any bypass capacitors at all, and I get gain, which is AV is 0.5 GMRC. I lost half, but we'll see later on, you can recover this 0.5 also. Through some modifications, you can recover this. So we have a stage. I'm pointing out to you, we have a stage like this, which does not require any capacitors here. No coupling capacitors, no bypass capacitors, and gives you high gain also. Now remember, I think you've all done the analysis. So you remember how we are achieving this high gain here? If you recall, we said that at this point, we need a very low resistance. So let's look at this particular stage here. At this point, if you need very low resistance, what have we done? We've connected another transistor where you are seeing the emitter. And when you look into the emitter, what do you see? A very low resistance. So that's the strategy that one has used. You've connected another transistor here such that at this point you are seeing the emitter. And when you look into the emitter, it becomes a very small resistance here, and which almost acts like a bypass capacitor. It plays the same role. So what it is doing is leading us into, when we have a stage like this, we can make it symmetrical. We have an RC here. We can connect another RC here. We have two bases here. We can apply a voltage here. We can apply a voltage here as well. A more general stage. And it's leading us to a stage which call it as a differential amplifier. A very, very important amplifier. If you want to implement circuits on an IC, you have to go and use at least one differential amplifier stage. Note that there are no coupling capacitors, no bypass capacitors, and this is the stage which is ideally suitable for implementation of an IC amplifier. All right, so that's where we are headed when we look at how do we implement things on an IC. Okay, another problem that I hinted at, can one get rid of Miller's capacitors? Note that when we look at a stage like this, there's a capacitor here between base and collector, which is C mu. C mu, and C mu is getting multiplied by the gain. So if you try, in a common emitter amplifier, if you try to build up gain, the gain gets multiplies with C mu and appears at the input and pulls the cutoff frequency low. So the issue is then I'm looking for an amplifier where I don't suffer from this Miller's effect. What is Miller's effect? Miller's effect is any capacitance connected between input and output gets multiplied by the gain and appears at the output, appears at the input here. It gets multiplied by the gain of the amplifier here. C mu multiplied by GMRC. So I'm looking for an amplifier which does not suffer from Miller's effect. In effect, what am I looking for? I'm looking for an amplifier in which there would be no capacitance between the input and the output. If I can find an amplifier in which there is no capacitance between input and output, then there is nothing to be multiplied by Miller's effect. And therefore, I would not suffer from that. So can I do that? So this is what I'm trying to eliminate. A stage where there is no capacitance between input and output. Well, look for an amplifier circuit in which there's no capacitance between here. Now, look at this bipolar transistor. We have to use a transistor. Is there anything in this transistor where there's no capacitance? There's a capacitance between emitter and base and collector. Are there two terminals in between which I don't have a capacitance? No direct capacitance between the two stages. Emitter and collector. There's no capacitance between emitter and collector. So can I build an amplifier in which what should be my output will always be taken from collector. Okay, output is always taken from collector. That's the reverse bias junction. That's where you get high output resistance and high gain and all that. So if this is the output, then I must apply input at the emitter side. Then I don't get a capacitance between emitter and collector. And that leads us to a common base amplifier. A common base, note that I'm applying input. RE, R1, R2, RC, these are all biasing. We are all familiar with. Okay, so don't worry about it. I'm taking an output from the collector. And I'm applying input now to the emitter. Applying input to the emitter. Base is now my common point here. So there is no capacitance between emitter and collector here. No direct capacitance. There's a capacitance between here and down. There's a capacitance between collector and base. But no capacitance between emitter and collector. So this will not have Miller's effect. Okay? No capacitance here. So we are arriving at common base amplifier in an attempt to get rid of Miller's effect. And we are saying, yes, this stage may give rise to an amplifier which doesn't suffer from there. And so it's a potential solution. Okay? Last problem. Problem number 5. Driving low impedance load for my common emitter amplifier is a big issue. Low impedance load. Why is low impedance load important here? So here is a example of, where I have some amplifier that we've designed. We put load resistance equal to 2.2K, and you can see all the numbers. Gain is gain, input resistance, output resistance, all of that you see. Okay. First of all, you note that already this amplifier is very inefficient. The power that I take from the supply is 46 milliwatt, and the power that I deliver to the load is only 0.9 milliwatt. 1 milliwatt of power. Imagine something which is so inefficient. 46 milliwatt you're taking from the supply, and all you're delivering to the load is 1 milliwatt. But anyway, we'll come back to that. So here the load resistance is RL is 2.2K. All right, so I get gain, I get input, output, all this they look reasonable. But I need to drive loads very commonly, loads which are low. They're not 1K or 2K. A loudspeaker may be only 8 ohms. A headphone jack maybe, 100 ohms, or depending on this thing. So the load resistance is usually small. Well, suppose I take the same amplifier and I collect a load resistance which is 22 ohm. Just take the same amplifier and I connect 22 ohms here. If I connect 22 ohms to the same amplifier, the gain becomes less than 1, swing becomes 40 millivolt, it just stops working. The whole amplifier collapses. The whole amplifier collapses because, gain is RC parallel RL, and if I make RL equal to 22 ohms, it just collapses. It doesn't work. So in order to make it work, note that what would happen is, why it collapses? Because RC is so large. 2.2K, and this is, RL is 22, and ICQ RC parallel RL, so the whole thing collapses. So if you want to drive low impedance load here, 22 ohms, then you have to make the output resistance here also low. Then only the gain will not collapse. So you'll have to make, instead of 2.2K, you'll have to use very low output impedance. So I need to make this comparable to this one here. So I can, instead of 2.2K, I can redesign the amplifier with 22 ohms. So 22 ohm amplifier, designed with an RC of this one. Look at its characteristics. Well, 22 ohms, still I don't get very high gain, but that's okay. 4.2, I get swing. Note, when you connect 22 ohms here, you're actually using, and all the resistance is so small, you're using very high ICQ, very large collector current. Very, very large collector current, because the resistances are small, the voltages are the same for the swing consideration, and therefore the currents become very large. Look at the power here, 3.47 watt of power, and power delivered to the load is 0.15 watt here. So what is happening is, if you want to drive a very low impedance load, then you have to use low resistances here, on this side here. You get into very high currents, and you get into very low efficiency, very high currents, very high power dissipation. So all this is becoming a problem when you want to drive a low impedance load here, 22 ohms. What is the solution? So what I'm saying is, why are you getting into this problem? If you want to drive a very low impedance load, you need to have very low output impedance also. So in that sense, very low output impedance here. So I'll come back to that. So these are the two things that are occurring. In that sense, a common collector amplifier makes sense for us. Why? I want to drive very low impedance load here. And we said to drive that, you need very low output resistance here. Now, when you look into this output resistance here, when you look at from here, what do you see? You're looking into the emitter. And when you look into the emitter, you get very low output impedance. So without really using very low values of RE, see, RE can be 1 kilo ohm. RE can be 1 kilo ohm, but when you look into the emitter, you'll get a resistance which is 10 ohms. On the other hand, if you go back and look at it, if you look at from here and you want 10 ohms, you'll have to connect 10 ohms here. And when you connect 10 ohms here and you have a supply voltage of 12 volts, you'll get very huge current. So in an attempt to get very low output resistance, which we need for driving low impedance load, we find common emitter amplifier is not at all suitable. Is not suitable. And in an attempt to overcome that, a common collector stage becomes more attractive, where you apply at the base here, but you take output at the collector side. At the emitter. When you take at the emitter, the output resistance is looking into the emitter, and that is very small here. So this is where we end up with. So in an attempt to solve those problems that you see here, we arrived at transistors, amplifiers with active load. We arrived at differential pairs, a common base configuration, and a common collector. So from next lecture onwards, we'll start looking at common base, common collector. We'll quickly do that. Then we'll go ahead and look at differential pairs, and then maybe a little bit more on active loads. And we'll be done with BJT amplifiers. Once we are done with BJT amplifiers, MOS is all similar. So it's going to be all a revision for you. Except that all that we have done with BJT, we'll again do it with the MOS. All common source, common differential pairs, all of that with the MOS stage here. Okay. So let me stop here.